you know, there were various people using it, and so I was listening to actually a sort of middle school teacher somewhere in the East Coast, some people at Johns Hopkins that use it, and some people at San Jose State that had feedback for me on how I give the review part of the grades. So how much is your review work, you know, worth? And so they had some very interesting feedback on their classes. So I was looking at their data, and then I decided to change the algorithm to actually a more generous one, basically for you. But the algorithm relies much more on listening on the review feedback. You know that grade between -2 and +2 that you can give on the reviews you receive. So that will now count as half of your review grade. Half is the accuracy of the reviews, and half is this thing computed from the +2 and -2s. To prevent, you know, some kind of tit for tat behavior, for if some of you receives a bad grade, I discarded the lowest of the grades of this feedback before I use it. Okay, but so that's what that's the change in the algorithm. I mean, I rely more on this feedback grade, and I'm more lenient when I compute the precision of the people grading, because it was, you know, I looked at some data and it was not very good what I was doing before. It was too harsh. Again, if you have complaints about specific cases, let me know after I assign those grades, and you know, I will take care of it and look at it. That's the only way I know. Actually, I can tell you one thing about the QuadGrader that is kind of funny, and I'm curious about your feedback. So, my student Michael Shavlovsky and I submitted a paper on some statistical studies that we did on how accurate it is. And it turns out that the best results we obtained them from an algorithm that considers all your grades, but weights them differently according to the accuracy of who gives them. Okay? This is not the algorithm I'm using in QuadGrader. The algorithm I'm using in QuadGrader actually throws away the least and the greatest grade before it applies, you know, some smarter weighting. And I do this just to give you, you know, some sort of warm, fuzzy feeling of confidence, so that at least one outlier is taken care of entirely, you know, no matter what the dark box algorithm, black box algorithm inside is not black box, is published, but maybe doing, okay? So if you have any feedback on these, essentially I lose a tiny bit of precision to give you a tiny bit of warm, fuzzy feeling. And I think it's a worthwhile you know, trade-off in practice, but I'm always open to feedback. By the way, the other lesson from QuadGrader that directly applies to your apps is this. You see, apparently I made a small mistake. I decided that one item of the rubric should be graded out of 4, the others are out of 2, and my UI was not perfect. You know, I should have indicated it in some more evident way what the grading range is. Okay? So a tiny problem in the UI reflects into a big problem in the usage. And I've seen these over and over and over, okay? And this is particularly problematic for me because as a designer or developer, UI is not my strong point. I find it difficult to, you know, I'm not a visual artist, and I'm not even though I have a highly visual memory, I'm not good at necessarily at designing this visual stuff. Okay, and it's a real problem because I notice this also in the Android apps I try to contribute to, that, or I see others that develop them, that very tiny changes in the UI cause actually very large differences in the way people use them. It's very, very difficult to make an app. I'm telling you, for your apps for the project. Some of you may be gifted, okay? But for those of you who are not gifted, who are just like me, it's a real problem because you get to, you know, 95% of the beauty and the functionality, and you reach 10% of the audience because all of the rest of the 90% think your app is too, you know, they can't figure it out, or they can't use it well, or it's very difficult to make something that can reach everybody well. Okay. I think for me one example was simply this feedback in QuadGrader. Now it's working half okay. For a long time, the percentage of people giving feedback was minuscule before I got some UI improvements. So you know, no matter how the smart algorithm is behind, which is, you know, sort of a territory I understand a little bit better, if the UI is not there, it's very difficult to make these things work. Okay, so just as a comment for your acts. I was giving advice to students today, and I just want to give you one general principle. Many of you know it, but essentially, when you develop your app, fight one problem at a time. So if you have you know, various pieces of functionality that you need, A, B, C, and then your app is wonderful once A, B, C are done, don't just code A, B, C that are all three of them difficult and hope that you get done with all three of them. Okay? Decide which one is the key, suppose it is A, and then do A, and get it to work. And find some way to just, you know, replace B and C with something simpler that is not really quite what you might have wanted to do, but, you know, gives you something that you can use, or test at least. You know, once A is done, then you move on to B, etc. But don't fight on multiple fronts, okay? Because otherwise, if you do A, B, and then, you know, they don't work, you know, it's very nasty to have to debug two problems, especially if, you know, without A and B both working, you can't really test your app in a decent way, okay? So I think this is very well sort of commonly given advice, but I think it's more commonly given than commonly listened to, right? I think that's a problem with all advice. Another thing that I would really like to do, and if you have suggestions on how to best do it, is this. I mean, there are a few things I would still like to do in a lecture setting. I would like to explain. Today we will be doing sensors, location and sensors. And then there is some material on views that I want to do. And some people were asking about databases and content providers. Okay, so these are still things that we may do. But I think in some ways it would be far more interesting for the class if you had some... if we could dedicate, say, the last 20 minutes or half an hour of each class to a sort of open setting in which you ask problems you have with your project, and then we all try to help. I try to help, and other people try to help. Because I think out of the advice given to other people, you would learn advice also for your app. So would you be willing to do this? And, you know, if so, would there be some volunteers, you know, 1 or 2 groups that want to go for next time? Let me know on Piazza, because I would really like to start doing sort of office hours in class, in a way, you know, because out of the advice to other people, sometimes you go much more in depth into particular topics than if I just lecture in this way. And I think it would be interesting, okay? Does anybody believe that this is interesting? I mean, by now, yes. And it would give us a change, you know, from these long lectures as well. So please, you know, volunteer for next time so that we can start doing it. And, you know, your app doesn't need to be perfect. You may be really fishing for how to best organize it. But these discussions may be interesting to many people, actually. Okay? So, so now let me go on sensors. So I have some slides, but also I'll have to point it at the whiteboard, because some of the things I want to tell you are slightly more complicated ideas that you don't need to implement in any project, but I just want to give you the flavor of how to really do things well if you wanted to do them well, okay, for some of these things. So let me share now with the desktop, and sorry, I'm going in circles. Okay, let's start with the location. Okay, so in location you can do it in 2 ways. So let me first some words on what's available on a phone. Okay, you get location on a phone in a number of ways. One of them is that, you know, you can switch on the GPS, and the GPS after a while it will start to give you fairly accurate location updates. Okay. The GPS has a startup time. It depends on the phone how long it is. It can be, you know, from anywhere from 5 seconds to over a minute if you are unlucky. Okay, so another location provider is done via cell towers. So essentially, the phone can make an estimate of which different cell towers are within the radius. Okay, I mean, which different cell towers are within reception radius, and how strong the signals are. Okay, I don't know. I don't think they can get also the angles of each tower. I don't think so, but I might be wrong. Okay. But out of that data, you can do some triangulation. You know, if you know where the towers are, if you know that one is here, and the other one is here, and if you know the distances, you know, if you are this distant from this tower, you must be somewhere here. If you are this distant from this tower, you must be somewhere here. If you are this distant from this tower, you must be somewhere here. And so then you have some sort of radius of uncertainty of where you might be. Okay. So depending on the uncertainties, you get a possible location. The same thing is done with Wi-Fi access points, okay? So Google knows where a lot of these Wi-Fi access points are, okay? So every Wi-Fi access point has an SSID, but also has a MAC address, and the MAC address is unique to the object, okay? So you can do the same type of triangulation. I believe, by the way, that the first time Google obtained this data via crowdsourcing. So essentially, if you had your phone on and the GPS on, or even the GPS off, but it would start, you know, as you wander around with the phone, it would start to get information about which SSIDs, I mean, which MAC addresses are in the neighborhood, and also which cell towers. And if you continue to send this information back from a lot of people that roam around with their Android phones, pretty soon you can build a map of the whole country. Okay, so as you know from the German controversy, Google was also getting some of these SSIS MAC address data for Wi-Fi access points via Street View cards, right? Because if you can get it in a more organized, it's simply simpler to process, right? The Street View card has a very accurate GPS, so it's just a lot easier, you know, than devising these crowdsourcing algorithms, I guess. But anybody who develops a new mobile OS as if that was an easy thing, but even if you develop your own app, you can actually start mapping around all the location providers in a crowdsourced way. Okay, so the main ways are cell towers. So cell towers is always available provided you have a SIM card in it. Otherwise, you can do the triangulation on Wi-Fi networks, and these methods have the advantage that are fairly low power, and you can you know, they're available with very short delay. Okay. And then if you want to wait longer with the GPS, okay? So the problem of location sensing in an Android app is essentially that you have many sources of location, and you have to sort of juggle which one you want, how precise you want it to be, with what delay you want it, okay? And how much battery do you want to use? GPS uses battery. Okay, it used to be pretty bad. Now I think it's a little bit better, but I don't know how long a phone generally lasts on GPS continuously on. Have you tried? I haven't in a long time. Yeah, it used to be like 2 or 3 hours. Now maybe it has improved. So, so you know, this hierarchy of location services explains the various ways to get location. So there is a way in which you get a fast fix. This is what I wrote here. Okay, so you get a you simply get say location is equal to location manager get last known location of a certain location provider, and you can use the network provider which is always on. It's a better idea to use the network provider because you are getting the last known location, and the last known location of a GPS provider maybe, you know, the last time it was on, so maybe you're 100 miles off. Okay, so this is very good if you need to have zero delay. If you, for example, if your app, suppose this is a typical use case. Your app is coming up, and you need to present some screen with some information, and then you know you are going to start a process which I will explain that will acquire a better location. But while that hasn't come up yet, what you do is that you use the best you have so far to give the best landing page you possibly can, and then you improve it. Okay, so that's a very common strategy. So location is equal to location manager get last known location provider. Location is not null because it can always be null please check that locations are not null, because they are null quite often. You know, location provider was down, the phone has just rebooted, whatever. I mean, you can never know when the location is null. But otherwise, you can do things with it. Okay, the location is a Java object, obviously, and it has various methods. I forgot all of them, but it's quite handy. The simple methods are latitude, longitude. It can have an altitude as well over sea level. And then it might even contain some speed indication of where we are going. Okay, so some bearing and speed at which you are moving. And it can contain other things. In part, it might depend on the GPS device. I would not swear that, you know, all the fields are available on all phones. But you know, you can look at the documentation for the location type, or we can look at it now for them as a matter of fact, I guess. And Android location object. Okay, and you would see in the reference, and you can see all the list of the methods. Okay, bearing to where it's going, it can convert itself to various things. If you have another location, you can ask the distance between a location and another one, which is really quite handy, because, you know, otherwise you have to use a little bit of trigonometry, because if you have to lat long to know the distance, you know, on the Earth sphere, even if you consider it flattened out, you know. But as you all know, you know, 1 degree of longitude is different at the equator or at the pole. At the pole is 0, obviously, you know. So you need a bit of that. Okay. So you can get the accuracy, you can get the altitude if available. Otherwise, you get I don't know what you get otherwise, because the returns are double. So I hope there is a method that says has altitude. Yes, there is has altitude, has speed. So you can do a lot of processing on these. Okay, so these methods are really quite well. I mean, these objects are quite well implemented. They give you a fairly rich, fairly nice set of methods to work with. So going back to the presentation. Actually, I should just push it. Sorry. I should just do this so it's easy to go back and forth. Okay. Oh, okay. I had it in the next slide. Sorry. Well, now you know where to get it as well. So the other thing that you want to do is this. You want to, if you want more than an easy quick fix, the typical thing is that you want to start to acquire locations. Okay, and what you do is that you start some location service. You need to declare it in the manifest, by the way. Okay, so there are these permissions that are access find location, and I think you can also ask for access to course location. The course location gives you the network provider, and find location gives you ability to switch on the GPS, turn on the GPS. Okay, so. But by and large, the schema is this. Okay, you are going to ask which location providers are available, if GPS or only network. Okay, most often you have GPS, but I think some tablets may not have GPS, so you need to ask. And once you know which location providers, you start a process that has a callback. So you start some, you give a listener. You start a process giving it a listener, okay, and your listener will be called back each time there is a new location available. I think you have seen this paradigm already in other places in Android, right? But we will see that most of the access to sensors works with this paradigm. So you build an Android object. It can be even the whole activity that implements a listener on location. I forgot, but I have it on the next slide. On location changed, I think it is. Okay, and this method on location changed will be called each time there is a new location available. Okay, so classical Java paradigm. Okay, so you get a location manager. Okay, and then you do this. You define a location listener, which is a new location listener, in which you define your own on-location changed implementation. Okay. So, and there will be a call to on location change each time there is a new location available. This can be, you know, 1 time a second or multiple times a second. I don't know. There is no guarantee. I think typically it's on the order of 1 a second at most, but there is no, you know, hard-coded guarantee of how often this happens. And there is also something that says on status changed. So this is a callback that will tell you essentially when services go up and down. So on status change, you may use it to display, you know, toasts that say, for example, I'm sorry, but your GPS lost, how it is called, the lost tracking. I mean, lost accurate. How do they say? The GPS lost its mind. I don't know. Okay. And so that's used essentially for this big, you know, big management thing. So you can also decide that your app should switch to another kind of algorithm if the GPS is lost momentarily, right? And the first one is called each time with new locations. So, so pretty simple. Once you define your new location listener, that is defined in that way above, you say location manager request location updates, and you say which provider you should be using, and you pass it to your location listener. Okay. And you can also register the same listener to more than one provider. This registers it to the network provider, but you can also register it to the GPS provider. I have to tell you that in general, there is a fairly complicated, you know, you may want to call it elaborate way of asking which location provider you might have access to. So Android defines, I don't know if I go in these slides or not, but there is a fairly complicated way in which you say, I want to be precise, but I don't want to use so much battery, and I want to use this and that. And give me the best location provider, and this gives you the location provider that is the best according to the principles you have said. Okay. Once you have this location provider, you can register to it and use it. Okay. So there is essentially this declarative way of getting the best provider. And then there is the brute force way, which is this one, in which you say, hey, give me the GPS, no questions, right? I don't want to, or hey, give me the, so what are the advantages of the two approaches? You know, the direct brute force approach is more direct, you know, you can implement some settings that says, you know, would you like to use GPS or not? And people understand what the GPS is, you know, they will either select it or not, but they know, everybody knows what is GPS, right? So if you use the direct way, I think, you know, things are generally simpler. The problem is that you need to worry whether the GPS provider really exists, okay, in each phone, because it's not guaranteed to necessarily exist. Yeah?
Well, is there a GPS permission you can use then people without GPS from obtaining an app?
Yes, there is. So I never mentioned this, but this is a very good question. In the manifest, you can declare also, there are two types of permissions, okay, if we go to the manifest. One is the use permission, in which you ask, please, can I use, can I access your contacts, can I access the internet, can I turn on the GPS? This is a use permission. But there is another type of permission, which is essentially used to filter whether to present your app to users, yes or no, okay? So if you have that, for example, you can make your app available only to people who have both a GPS and a camera. Otherwise, they don't see your app on the App Store. Okay? Use it very sparingly because, you know, I personally think it's better to try to find any possible way out, but I think it's better to present your apps to a broader audience as broad as you can. Of course, if you need to take photos, you know, it doesn't make sense that you don't ask for the camera to be present, but aside from that. The problem of the more general approach, and this is again one of my purely personal digressions, is that these declarative approaches are very beautiful, but in practice, you know, you never know how precise you want to be. You just want that you know the GPS because you know what the GPS is, right? I mean, it's a little bit difficult to always declare what your long-term goal in precision is. It reminds me, these investment advisors that ask, for the first questions they ask is, what's your investment horizon? And you want to answer them, well, if I knew, it's like if I knew my horoscope, what do I know what will happen to me in 10 years? I mean, this is a completely silly question, in my opinion, right? And so, is this question in which, if you knew the ultimate truth, then you could take the trivial decision. Yes, right, but it's easier to take the trivial decision than to know the ultimate truth, right? So, I mean, it's easier, in investment, it's easier to know a simple answer than, your life path in 10 years. So it's completely crazy, in my opinion, that they start by asking those questions. But at any rate, okay. They should apply more stochastic processes and ask, what's the distribution of probabilities among different destinies? Okay, so jokes aside, I mean, digressions aside, you register your listener, okay, to a location provider, and you can also stop it, okay? And you should stop it. In fact, you should remember to stop it. It's important, and you should do it typically in the on pause or on stop methods of your activity. Okay. Now, this slide is ripped out of the Android. There is a nice tutorial on locations, which I think I linked in the slides, but otherwise I will link in the website. This essentially tells you what might happen in an application. You start it, you listen for GPS and network updates. The first update you get is usually stale. The location provider first gives you whatever is available last, and then tries to do any better than that. So you may get a cached network location, which is usually not that bad, because the network is always up. The cached GPS location is dismissed as too old, but you have to dismiss it. I mean, the problem that this slide is highlighting is that you are fed all this information, and this information mixed with garbage, okay? And it's your problem to actually sift the information from the garbage, okay? And Android does not do a lot of this for you. It would be nice if it did, but it doesn't, okay? So it essentially gives you, in the order in which they come, the best updates. So for those of you who are here, let me just visualize what might happen, okay? You may get a network update. Then you may get a GPS update that is like 2 miles away, or maybe 20 miles away. Then you get another network update. Then you get another one of these, we always have some sort of big circle to it, And then you get another of the network updates, and now, this starts to converge and has a somewhat smaller circle. And so you get sequences of these point with a ball around it. Point and ball, point and ball, point and ball, coming from different places, okay? The ball is the correct topological term. Okay, and so you get a sequence of these, and now you have to do essentially what is called sensor fusion. So you need to reconstruct out of this sequence the most likely update for where you are. Okay, and this is a problem that it's difficult to do perfectly. And actually, it would be worth some digression. And maybe if you are interested, we can do a lesson on sensor fusion later on. Actually, it would be sort of fun. The right approach would use some sort of probability theory, okay, and Bayes' theorem. How many of you are familiar with Bayes' theorem? So let me give the very quick gist of it, okay? But in a Bayesian set, let me just maybe stop the recording so that I can. I mean, not the recording. Stop the. So the screen share. No, not chat. Screen share. Okay. Yeah. So, how can this work? Okay. Imagine that you have some location which I call how do I call a generic location? I call it X, but imagine that X is a vector. Okay, so X is a position. So imagine that I have some probability of x that tells me where I'm likely to be. Okay, this is essentially where you were in the previous moment, okay, or your previous estimate. And now I want to describe to you how you could essentially update the probability of where you are in a Bayesian way. So essentially, Bayes' theorem can be written in this way, that the new probability of being at a place x is proportional, okay, to the probability of having an observation obs given that you are at x times the old probability of being at x. No, sorry, did I get it right or not? Hold on, I almost get it vice versa. So P of A given B is equal to P of A B divided by B. This is how you. I never have any memory, so the way I became good at math, I think, was by deriving things on the fly. Okay, and so this is probability of B given A divided by P of B, which you don't care about, times the probability of A. Okay? So everybody agrees with this. And then we throw away the denominator. So what I wrote is correct. So this is a probability of observation given x times the old probability of x. Now let me tell you what this means. So now you know how to derive Bayes' theorem if you ever forget it, as I always do. Any objection? No. Great. Great. So how do you use it? Well, the fact is this. For a typical sensor, the probability of observation given x is easy to know. This you are told by the manufacturers of the sensor even. Okay? So when you have a GPS, this is a probability that this is the reading given that this is the truth. And the GPS sensor manufacturers can tell you this. Okay? The output of the GPS is typically a location with a radius of uncertainty. So this function here, you know, the probability that you are a y given that at x is generally proportional to, I'm inventing, okay? But it will be something at e to the minus, you know, the modulus, the distance between x and y squared divided by some radius of something related to the radius of uncertainty. Okay, so this is proportional to something like this. Okay, so it will be some Gaussian shaped in that way, right? Centered at the point. It will be a Gaussian distribution centered at the reality, and you know, with an amplitude, with a width that is related to the radius that the GPS object gives you. Okay, so this is known, and this is known as well. It's the distribution of the location. Okay, so in a trivial way, if you have an old probability distribution for the estimate and you have one more observation, you can compute a new observation, a new probability distribution. Now this is not quite right, okay? Because the problem is that not all these observations happen at the same time. But so if you wanted to be smart, okay, you could do something like this. You could say, okay, I can do an update in two steps, okay? So I have, so this is my algorithm. Sorry, let me, this, yeah. So this is my algorithm. It works in this way. So P0 dx, okay, is equal to something. Okay, I don't know what it is. It doesn't even matter very much. You can get a wide Gaussian on your initial distribution, because in that way, you know, you're safe. It doesn't matter so much because you're going to refine the position. So even though at the beginning you're not precise, you're okay. Then you repeat the following. P k plus 1, I call it with a hat of x, is equal to P of x with two things applied to it, you know, shifted, maybe let me write it in this way, P of x plus v plus delta t, okay, So if you have information about the speed at which you are traveling, you can just assume that you have been moving in a straight line. And delta t is the interval of time from the previous reading to the current reading. Okay, so you're just shifting the distribution. Okay, plus, and it's not really some plus, so let me write it in this imprecise way. Okay, but widened by a factor dependent on delta t. The point is this, okay, that if you were traveling at speed delta t, sorry, at speed v, which may be done only with some precision, 1 second later, you're still likely to move, to move around the speed v, just because you cannot accelerate too fast, otherwise it's uncomfortable. So nothing, if you're not a known person, but essentially, it's reasonable to assume that v doesn't change so much. But if this observation is, a minute old, in a minute, your speed could have varied a lot, and so you need to essentially take the old probability distribution, shift it for the speed, and then broaden it to reflect the uncertainty about the speed that might have happened in that delta t, okay? And then, once you do this, you can say that the true period k plus 1 of x is equal to this p hat of k plus 1 of x, so the shifted one. So this approximation you obtain it by factoring the speed, okay? And then once you're here, you multiply it by probability of the observation given x. Okay, so you apply bias and state in this way. Okay? And you can also do this in a slightly more sophisticated way. Okay? And the slightly more sophisticated way is that in this place, if you ever want, you can put in a little bit more knowledge about the state of the world. What do I mean with that? Now, apps like Waze have become a lot better at doing a prediction of where you are. But even the old Google Maps used to be pretty bad. I live on the other side of the hills. I live in Silicon Valley, so I commute here via Highway 17, and sometimes, I'm there, navigating these turns at around 50 miles an hour, and then Google Maps believed that I suddenly was traveling at 50 miles an hour in a tiny nearby street that just happened to be very close to the highway. This was completely absurd, because the probability that you are able to jump from the highway, if you are on the highway, with a very high probability your next location is going to be either on the highway or on an exit ramp. Okay, its probability very close to 1. Okay. So and also the probability that you're traveling at 50 miles an hour on one of these tiny streets is next to 0. So if they had a better model of how to do this probability that you observe that given x, or maybe this Bayesian update, that would have been the place where to put it actually. They should have done this Bayesian update based on the speed, taking into account that you most likely are not leaving the roadway. Okay, so this step would have constrained you to the street, and this step would have told you where in the street. Let me give you a picture of how this double update happens, okay? So imagine that you are on a highway, that this is a highway, okay? And imagine that I'm here now. My speed is this, okay? So imagine that you apply these 2 steps. My location is pretty well known at this point, okay? So I get the next update after 1.5 seconds, I may be here at that point. And this gives me, because I could have changed the speed, so this is pk. This is p hat k plus 1, where I just apply the thing of the speed. But p hat k plus 1, this is badly drawn. In reality, this is only on the street, right? Because this update here constrains me to a roadway. Is where I might be if I hadn't had the next location fixed. Okay? Then I get my next location fix. Okay? And the next location fix is going to be precise, but in a circular way, because the GPS does not know about road, and the precision of the GPS is circular, right? So then you get another update that is done. I wish I had a different color chalk, but I don't. Okay, let me do it dotted. Okay, the GPS is dotted. So the GPS will give me that I'm very likely to be around here, and somewhat less likely to be around here, and somewhat less likely not to be even around here. So now we have this narrow sector on the road, but imprecise longitude with respect to the placement on the road, and this other GPS that has another shape. If you do the product of these two, you will come up with a distribution that has most of the mass over T. Okay? Essentially, the GPS will tell you how far you are, and the other update will tell you that you're on the road, essentially, and they will combine. Okay? So this is a way to do sensor reconstruction for location data. Okay? Few people do it this in such a sophisticated way, but it's not that difficult to do. Okay? Actually, the only somewhat difficult step is this. You cannot devise easily a computer program to keep a representation of P of X for every possible location X. No, I mean that's a surface. So the one difficult decision that you need to do is that you need to decide how to sample your state space. Do you want to have a dot every square yard? Do you want to have a dot every on the road every, I don't know, every 10 feet and be done with it? That's the one decision that is difficult. But I want to stress that it doesn't matter incredibly how you sample it. Because, the beautiful thing about this theorem, this method, is that all my equals, in a sense, are proportionality signs. You just compute, for example, if you're computing this, you just compute the discrete points in your sampling grid, and then you normalize so that it sums to 1. Okay, so it's a fairly simple problem. You don't need to be, you don't need to say, oh, but what is the volume of this strange piece of space in which I don't know what? It's a simpler problem than that. You can just, overlay a sampling grid, work on the sampling grid, normalize so that it sums to 1, and be done with it. And it works relatively well. Okay, as long as your sampling grid is somewhat uniform. Okay, so this is sensor fusion for location. Let me go a bit on with any question on this. Actually, this is I think this is a digression from P100 development, but I think it's pretty useful. I don't know that you're told these kind of things easily, but this is an incredibly useful principle in many applications in which you deal with the real world. This is, I don't know, it should be taught in, I don't know, probably in your physics classes, really, it would belong somewhere. Essentially, it's a very basic problem. You never can measure anything with infinite precision. Okay? Anything you ever try to do with sensors is going to have some imprecision. And it's very common that you have a stream of this data. And so the question is, how do you reconstruct a maximum likelihood reality or data that you can use? Okay? So this gives you the update. Okay. Let me restart the screen share and go back. Okay, so this slide essentially tells you some of the same. So the problem is that the location services can become available and disappear. Everyone has their own precision, etc., etc. So we are not gonna do. Now, this example of finding the best location, I'm not gonna describe it. I think the most of the value is that you can look at the code and use it as sample code. Compared to what I was doing here, it's fairly horrible. Okay, so the approach I was drawing here is much better because it uses it's much more principled. Okay, this approach you see is basically a hack, but 90% of the people I think are doing hacks. So you can look at it up on the slides if you want. This is an example of how you may want your timeline to be in an application. The application starts, the user begins content creation. For example, you can start typing a comment, taking a photograph, etc. And at the same time, as early as you can, so the trick is to start the location service as early as you can, so that you hopefully have a good fix by the time you actually need it. Okay. So the user submits a record of the input much later, tagged with the location, and you stop listening to the updates. So the idea is essentially a complicated slide for a short content. Start as early as you can, so that you hopefully have a precise location by the time you need it. Local recommendations. Okay, fine. What about testing? So this is one of the cases in which testing is fine to catch the big errors. Okay, as soon as you have an application that needs to play with the location, it's invaluable, in my opinion, to really test it on a phone and to try, to do various things. Like, you walk around, you get in a metal elevator, you get out of the metal elevator, you drive a car, because it's very, I find it very difficult to predict the quick behavior of reality compared to what you can simulate in the simulator. But in the simulator, actually, it's pretty nice. You can go on Google Earth, okay, or any other place. Like Google Earth is free and is great. You go on Google Earth and you define one of your, or maybe you go running with your phone and you record that track. Anyway, you record that track. You can either walk around with your phone, or else you can, draw a track on Google Earth, which is very useful if you want to simulate that you go to places where you actually don't want to really go, okay? Because you're testing it, for example, how would it be to find, I don't know, restaurants in Las Vegas, but you don't want to go to Las Vegas every time you want to test. So you want to make some artificial tour of Las Vegas and use that, no? But once you have one of these location traces, you can load it in your simulator in the DDMS tab. I don't remember what DDMS is for, but it's a sort of device and something else. It's a tab of Eclipse that gives you access to your device. You can essentially feed it the GPS track as if the phone was moving, as if the emulator was moving following that track. Okay, so it's fairly nicely done. It's very useful to test these. Essentially, it's very useful because it's very repeatable. So at the beginning, when you want to test for your bugs, it really helps that your application always crashes in the same spot, so you can run it multiple times until you fix it. Repeatability is the advantage. Okay, so I think it's the end of this presentation. Yeah. Okay. Great. I have another one on general sensors that I would like to talk about. Any questions so far? Yeah? Yes, I'm saying exactly that. I mean, I'm saying, for instance, that you could decide, I'm just making a completely out of thin air example, okay? But if I were trying to do a service like this and I were trying to do it well, okay, I would do something like this. I would use the following grid for locations. I would take every known street and I would put a point, a dot, every, say, 10 feet. Actually, I would probably use 10 meters, or no, 1 meter. I don't know, some international system unit. I think they might work better with a GPS. I'm not. Anyway, I would put a grid on it. Okay. Then I would put another grid on it on the whole space of lat long, because sometimes you get out of a street and you go in places where there might be a street, but I don't know there is, or you may be hiking, for all I know. So I would have another grid. Okay, and now the point is this. Let me draw in another place because it is getting kind of crowded. Okay, but suppose that you have a certain grid, okay, of locations. It does not really need to be very regular, but it can contain, for example, the street that leads to it in this way. Okay. So at this point, every one of these points is a coordinate, okay? And I can decide that I do these updates, so I really compute these probabilities for every x, not for every x because there will be a huge number of them. But I would use some heuristic in order to cut off this probability distribution where it's low enough, okay? But then I would get numbers for each one of these points. So I would get, 0.1, 0.01, 0.2. And these numbers, if I just do the multiplications in this way, would not sum to 1. Okay? Because if you take the product of probability distribution, there is nothing that says that they sum to 1. In fact, the bias here has a denominator. And one of the tricks that I think might explain to you, but I'm not sure if you take probability theory, is that you normally don't worry about the denominator. because it's a constant, right? So you computed the numerator for every values of x that are interesting, and then you just normalize by ensuring that they sum to 1. Okay, so I would compute the probability at all these points, making sure there are not too many so that the problem is manageable. You know, the ones that have too low values, I throw them away, and I know how far I have to look, no? And then I would normalize to 1. And then, you know, what do you do once you get a distribution? Because to the person you have to show only one location. I think I don't know what is the best. There are two theories. One is that you give the mode, that is the point with the highest value. And another theory is that you could do the weighted average of all these points, giving to every point a weight that is equal to the probability. And I think it would be a little bit better. Okay? So, yeah. But yeah. So this computation is complicated, which is why many people cut corners. But
how do you generate those documents? Like, I understand
it's a data structure, right? For me, one of these documents will not be generated, but it will be a point of the form, highway 17, comma 2314, where these may be the number of meters from a reference marker on highway 17. I mean, I would have to have my own system of reference.
How would you, I mean, say you want to go out and do that all this stuff, find those sellers or something?
No. This is a symbolic point.
Right.
How do I know where this point is in 3D space?
Yeah.
No, yes. I mean, if I wanted to do something like this, I would do the following. Okay, I mean, this is a conceptual experiment because I have not done it. But the way I would do is this. I would look at the OpenStreetView. Oh no, OpenStreetMaps. Okay, OpenStreetMaps is this project. I think it was started in Germany, where they decided, and I completely agree with it, that having openly available information about maps would be a great goal. Google Maps does not give you the information. Okay, Google Maps enables you to render a map, but it does not tell you where the underlying roads and streets and whatever else is. So get OpenStreetMaps. Okay, you can download the data. Maybe you have to pay them a bit to contribute to the project, do it, etc. Once you get to the metadata, a street like Highway 17 has a representation. I have not looked into how it is represented, but it may be represented as a sequence of segments. Or some such data structure, where each segment has endpoints that are represented by lat long and altitude. No? And so you use that information to build this set of points on the streets. But you need to do something like that. So in fact, OpenStreetMaps is a fantastic project for developers, right? Because it really gives you the semantics of the real world. Unlike Google Maps, which has some great services like geocoding and reverse geocoding, but on Google Maps you can't really implement a system such as give me a way for you to walk to San Francisco. I mean, they tell you the answer, but you cannot compute it by yourself. Okay. Any other question? Okay. So sensors. Okay, so what are the main things for sensors? So sensors mean things like accelerometer, gyroscope, compass, gravity sensor. There is a bunch of those, okay? So there is a sensor manager that essentially gives you some information about which sensors are available and gives you ways to access the various sensors. Then you have a sensor, which is a representation for one of those sensors. And as usual, you have a sensor event that is an event like an update of a reading from the sensor, and you can define a listener. So we will see how they work. This slide is basically there so that you can click on these links and get to places where these things are described actually. So there are many types of sensors, okay, and more continue to come out. This is some representation of which ones are available by API. Accelerometer was always there. Ambient temperature, I don't know how precise it is. I don't know how much is ambient versus phone temperature. There is gravity, gyroscope, there is light, linear acceleration, magnetic field, orientation, pressure, only some phones have it. Proximity. Proximity is, every phone I've seen it has only two proximities, 1 meter or 5 centimeters. So it essentially tells you whether you're holding the phone to the head or not. It's basically just two values, but it's, useful. Rotation vectors, temperature. By the way, you have also some other sensors that are not really listed here, but that I found useful myself. But they're like they are not available via these. But I just mentioned them. It's sensor, battery level and battery temperature. So the battery generates some broadcast intent that you can listen to when it changes level in a macroscopic way. There is like normal, low, extremely low. If you want to be notified, you can listen to those broadcast intents. Otherwise, every now and then you can actually read the battery level. It gives you a number between 0 and 1, and you can also read the battery temperature, which can be useful if you I don't know, want to do if you want your application to decay gracefully, for instance. Suppose that you want to not just stop using the GPS if the battery is low, but maybe you want to do less processing. The lower you get, you can tune the things yourself. Fine. Okay, so listing the sensors, you say private sensor manager, my sensor manager. My sensor manager is equal to get system service sensor service, and then you need to ask for the device sensors is equal to the my sensor manager get list of sensors. Okay, so there is a way to get the list of the sensors. Okay, and then you can test. Oops, sorry, this is scrolled. I just wanted to. So my sensor manager get default sensor for magnetic field. If you want to sense for the magnetic field, you can get the sensor magnetic field and check whether it's null or not. You need to do it, unfortunately, because you never know whether there is a particular sensor on the particular device you're using. But if you are lucky, you have it, and if you are unlucky, well, then there is none. Okay. Here is an example of sensor selection. So sometimes I think the only message this slide has, and then you can look at it if you want, is that sometimes you can make it do with the different sensors. So if you have all the sensors, you have a lot of redundant information that you can use to your advantage. Okay, but sometimes, for example, in this case, if you don't have the 3 gravity sensors, you can use the accelerometer instead. So there are ways to get around that. Okay, you need to implement 2 callbacks. Okay, on accuracy changed and on sensor changed. Okay, so sensing motion. This is an example. We are getting all this code is doing is getting a sensor of type accelerometer. I hope the code is checking somewhere else so that the device is not null. Okay, so there is some description, okay, of the values you get. So typically you get, because the sensors measure a lot of different things, so they give you a very generic object, which is called sensor event, which has a vector of values. Okay, and it's up to you to know what they mean. They don't come with beautiful names. So if you have an accelerometer, there is this documentation that tells you that 0, 1, 2 means in the axis x, y, z. Okay, so there is documentation, but all you get is a vector of numbers, and you have to make sense of them. Okay, finding gravity from acceleration, gravity sensor, and I think I want to do this in a slightly different way. Okay, I want to show you some example of these sensors while we talk, because otherwise it's more it's kind of boring. 1 second. 1 second. I need to find the right app. So, okay, for the people who are watching these from the video, this is called Sensor Kinetics, this app, and I like it a lot. And let me just optimize how this looks. Okay, so this is listing all the sensors that I have on this phone. It's a Moto X. So let's see, I have an accelerometer, which gives me the acceleration in the 3 coordinates, okay? Now, if you read carefully, actually for you is bigger, you see that there is an acceleration on the z-axis equal to 9.9 on average. What the hell is that? Gravity, okay? Because this sensor is a pure accelerometer and measures essentially the force exerted on a mass. No? There is a mass somewhere. I don't know how it is realized, whether it's in silicon measuring the bending of the silicon or how. I assume it is. But I assume this accelerometer sensor has some very thin ledges of silicon that have been cut off, like, you know, very long trampolines, sort of, in the 3 axes, right? And they are thicker at the end, and they get bent ever so slightly by any acceleration, and you can measure how much they flex. And so you can reconstruct the acceleration in the 3 axes, which are the 3 axes of the phone. So now there is gravity there, and that 0.2 is because my phone is not flat. Actually, if I probably could make it flat somehow, I don't know exactly how, but maybe this way. Yeah, well, I don't seem to be able to. Okay, this way, more or less. But you know, if I tilt it more brutally, then now there is also acceleration in the y direction. Okay, so these are really the 3 acceleration in the 3 directions. Then there is a gyroscope that gives you essentially the unit of rate of turning around the 3 axes. Okay, the speed of turning around the 3 axes. Okay, it gives you also the precision, etc., etc. Notice how high the hertz rate is of these sensors. It's really beautiful on this phone. Then I have a magnetometer that tells you essentially the direction of the magnetic flux. Okay, now this is very nice, but of course, sorry. Of course, having the accelerometer that contains gravity is not so nice, okay, for many applications. Because if you're trying to track where the phone is, you would be better off without gravity, okay? So how can you eliminate gravity? Well, what you do is essentially that you implement a sort of very low pass filter. So you say, okay, gravity is what is always there. So that, you know, if I shake the phone in some way, imagine for the moment that I don't rotate it, the z component goes up and down, but if you take the long run average, you would get gravity, and then you can subtract it out, okay? So we did some process that essentially does the following. It takes into account the accelerometer and the gyroscope, it tries to reconstruct what this phone is doing, and then it tries to subtract away always gravity to find the rotation and the acceleration without the gravity in it. Okay, that is a sort of the useful information that it might be easier to use. Yes.
So, what directions are X, Y, Z for a phone, especially given that you have to?
The X, Y, Z are tied to the phone. So, so Z is this, Y is this, and X is this. Sorry, yeah, I'm very useful.
So X, Y.
I mean, this is my phone, okay, with but. You know, with the 3 buttons on here, no? And this is the loudspeaker, okay? So this is X, this is Y, and Z is poking out, okay, towards the face of the phone. Okay?
So the same X and Y is like a display.
Yeah, I guess so. Yeah.
So you would pick the phone all the way up and have it go to 9.8, 9.9?
Sorry?
You would stand the phone up?
Yes. In fact, I can probably even do it if this can rotate. Yep. Well, okay, sorry, I have to keep it steady. It should focus. Does it? Or do I need to be further? What does it say? I may need to keep it more vertical. Okay. Now, sorry. Okay, the derived sensors, okay, that are computed for you are called. There is a gravity sensor, okay, that tells you essentially in which direction is the gravity. Okay. Then there is some linear acceleration, which, you know, if I leave the phone quiet, it should be always 0, but there is noise in the sensor, so it's hovering around 0. But that is what you would be able to use in order to do the the interpolation of where the phone is. And then you have the rotation sensor, which is similar to the gyroscope. Okay, but it's so. Why do we have raw and computed versions of the same sensors? Essentially, the fact is this: raw sensors are much higher in hertz, okay, in updates per second, but they contain gravity, and the data is not cleaned for you. If you know how to clean the data, you may be better off using those, because at least you know perfectly what you are doing, right? If you want to do something sophisticated, it often pays to go back to the original sensors and develop your own algorithms, because you know that there is nobody else tampering with the data before you get it. It's a huge advantage. The fact is that we don't know entirely how we get these derived sensors. So there is somewhere a long-running algorithm that reads these sensors and tries to improve them, okay? But these algorithms may, from time to time, make some update or some calibration to the direction of the gravity, to the calibration of the sensors, etc., etc. So on the, these data may contain some jumps at times due to the algorithm that is used to clean the data. There is that in between. Ambient and temperature, I don't have it. Proximity sensors, you see now it's 1 meter. If I put the finger there, where somewhere, I don't know where. Hey, here. Why doesn't it give it to me? I think it's here. No, but it always says, yeah, I don't know why it says 0 hertz. But this used to work. And if you go here, it gives you a graph, essentially. It seems to be broken. It's not broken on the phone. It's broken the reading on this app, probably. Oh, now it reads at 5 hertz. Okay, let's see whether it works. No, I think it's broken. Sorry? Oh, yes. Okay, now it works. 100 centimeters, 3 centimeters. Okay, there is a light sensor, pressure sensor, relative humidity is not available, etc. Now, some of the most interesting things here are, looking at the graphs. For example, let's look at magnetometer. We can look at the graph. Hey. I'm sorry, this used to work on my old phone. Let's see. Oh no. What is it, that they want me to pay? No. Oh, that I have to press start. Oh, yes. Okay. So this gives me the magnetic field in the 3 directions. Can you see it? These 3 lines. Okay. Now if I turn the phone, it's giving me the various projections. Okay, so there must be I could look at the rotation sensor. I can also look at the accelerometer, for instance. Okay, so two are close to 0 and the other one is stuck to 10. Now I give it a small jingle. And of course, if this was perfectly precise, the areas would be the same of the positive and negative. But maybe they are not, because there is some imprecision in the sensor, in the sampling. If I made a sweeping movement like this, I would probably need to let me see if the derived sensor are more precise, because to plot, because you can at least see only the they are close to 0, so the scale is better. Okay. No, how do I change the scale? Oh, it was so simple. Okay. So if now I do some movement like this, I should be able to do something. You see that it's not incredibly precise. Now, actually, I want to see back on this particular phone how the accelerometer is. Now that I can change the scale, I can look at it in detail. But it brings me back the old scale. Maybe I can eliminate the Z. No, I cannot. Okay, it works with more time precision, but it's not exceptional. So at some point, a student wanted to do an app in which they could draw in the air, and then this was drawing, on a surface. It kind of worked, but it was not completely precise. So if you pick up the phone and use a gyroscope, a rotation, gyroscope and accelerometer to move the phone around for a while, you don't really get. After a while you lose consistency. So if you pick up the phone, draw in the air, and put it back, you may believe that the phone is about a meter away from where it started. The location is harder. Instead, the gyroscope is a little bit better in the long run because it uses gravity to know the orientation. So it sort of autocorrects itself in the long run. So it's not that after moving for a long while the phone will be believed to be sidewise, right? Because it uses gravity to self-orient. Essentially, it uses gravity as a long-term correction for its own rotation data. Yeah, okay. So but this example that we have in code. Sorry, I need to read. Oh, sorry. No, that's not what I wanted to do. Okay. I did something wrong, and now it's. Okay. Well. Okay. So this is an example of filtering gravity waveform acceleration. I don't think you may want to implement it, but I think the value of this is simply for you to look at how to access a sensor, right? You are given a sensor event, and then what is it doing is actually something very simple. You are doing an average over a time window of the acceleration. So every time you say alpha times the old value of the gravity plus 1 minus alpha times the new value of the acceleration. Okay? It's sort of the other way around from the way I would have written it. I would have written 1 minus alpha the gravity plus alpha the new value, but with alpha very small. I'm sure that you want a smaller value than these, or a larger value in the way they used it. Okay? So first you do a long-running average to isolate the force of gravity with a low-pass filter, and then you remove the gravity contribution from the sensor readings. This is a very simple way of doing it, but it's just to show you how to access sensors, right? So basically you say on sensor changed, sensor event, and then event.values gives you access to the various values. That's what there is to it. Now, Linear acceleration is acceleration not including the gravity. Okay. Yes? Sorry? Maybe. It seems to be going on. Hold on. Now, how do I go back there? This way. No, this way. This way. Okay. The gyroscope gives you the rotation along the three sensors, and here is some example of code. But essentially, the update, actually I had it on a page here that I wanted to show you. So these are on the sensor of motion, and sorry, where is? So there is also a step detector apparently, but okay, this is the code I wanted to show you. So this code is called. It's in this section using the gyroscope, and if you go down, essentially. You are doing two things, okay? You are building a rotation vector using the gyroscope. And then you are getting a rotation matrix out of the rotation vector, and then you are updating the rotation vector itself. So there are, you have, you keep always a delta rotation vector. Sorry. You keep something like a rotation current, which is a vector that tells you how you are rotated right now with respect to the frame of reference. You know how much you are rotated around the x, y, and z axis. And z axis, okay? So these three rotations describe the orientation of your phone. And the point is, how do you update them given the reading of the gyroscope? And this sample code teaches you how to do it, okay? So you first read the rotation, you get delta t from the difference because the gyroscope gives you a rotation speed. So you need to know that delta t, which is a difference in time, as a difference between the two timestamps, and then you read the three speeds of rotation. Okay, then you normalize them to get a rotation vector. And then you get a rotation matrix that you apply that tells you how to apply this rotation to the previous rotation. Okay, so if you know how you have rotated, you need to get the matrix that is able to transform the previous vector into a new vector that is rotated by that amount. And so that's what you do here, and then you can update the rotation information for the phone. Okay, so. I mean, I could go in more detail, but I'm not sure exactly what you plan to use and what you plan to do with it. So, so maybe I should stop here actually and ask if there are any questions. I'm happy to elaborate on any topic, but. We could also read this code in detail if you're interested. Yeah.
The delta rotation matrix, why does at least why does that code have 9?
Because it's a rotation that is then multiplied by a vector to give you the new vector. So it's a matrix in the linear algebra sense. Oh. Okay. You have a vector that describes the rotation of the phone, and now you know that the phone, compared to that rotation, has rotated some more in some way. And so you need to multiply the matrix by the vector to get the new vector. Okay? And so Android helps you by enabling you to get the rotation matrix from a vector, in which if you say how much more you have rotated, okay, if you give it this delta rotation vector in input, it gives you this delta rotation matrix in output. And this delta rotation matrix is a matrix in a 3x3 sense that multiplied by the old rotation vector gives you the new one. Okay, and so it's hidden from you, you know, how to do. Yeah. And then there is some more sophisticated part in which I'm not getting into these. And so the more sophisticated part is that this delta rotation vector that they are building in order to get the rotation matrix is built using quaternions, which is a way to represent rotations in 4 components. That is more stable with respect to singularities than using the 3 components. So it gives you, you know, better uniform representation. Questions on sensors or on so there are lots of interesting things that one can do with sensors, quite obviously. Some of them require some more sophisticated algorithms, but for example, the step sensor is derived, obviously. You can get it from the accelerations by implementing some kind of filtering by which you can see if the person is walking, if there is some gait, and you have some periodicity, and you count how many oscillations according to that period. I think it's done that way at least. Do I have it? No, I don't think so. No. Any other question that you might have on the project or on anything? See, do I have a step sensor or not? No. Anything else you want to do? I mean, otherwise we see each other next time, I guess. No. Okay. Well, see you next time then.